Morning class. Yesterday we have started the chapter chemistry of p block elements, and we're studying about group 15 elements. And in group 15 elements we have come across the general introduction of group 15 elements, and after that we have seen about nitrogen and ammonia gas. Now today we are going to see about oxides of nitrogen. Nitrogen forms a number of oxides in different oxidation states, and they are nitrous oxide. You can see the Lewis dot structure, and it is prepared by heating ammonium nitrate. So ammonium nitrate on heating gives you nitrous oxide and water. Nitrous oxide is also known as laughing gas. It is a colorless neutral gas. Next, second oxides we have got is nitric oxide, that is nitrogen 2 oxides. It is prepared by treating sodium nitrite with acidified ferrous sulfate. So when sodium nitrate reacts with ferrous sulfate in presence of sulfuric acid, it gives you ferrous sulfate, ammonium bisulfate, water and nitric oxide. It is a colorless neutral gas. Next, the third type of oxides of nitrogen is dinitrogen trioxides. Nitrogen 3 oxides we call. It is prepared by treating nitric oxide with dinitrogen tetraoxide. So when nitric oxide is treated with N2O4 at temperature of 250 Kelvin, it gives you N2O3. It is a blue solid with acidic nature, and the structure you can see on the screen, the Lewis dot structure. Next we have got number 4 is nitrogen dioxide, where we have got the oxidation state as 4, nitrogen 4 oxide. It is prepared by heating lead nitrate at about 673 Kelvin. So when lead nitrate heated at 673 Kelvin, it forms nitrogen dioxide, lead oxide and oxygen. It is an acidic brown gas. Its structure is given below, the Lewis dot structure. And the fifth type of nitrogen oxides are dinitrogen tetraoxide. It is prepared by cooling nitrogen dioxide. So nitrogen dioxide on cooling will give you N2O4, that is dinitrogen tetraoxide. It is colorless solid or liquid with acidic character. Its structure is given below. You can see the structure. These are the two possible structure for dinitrogen tetraoxides. Next, the sixth type of nitrogen oxides is dinitrogen pentaoxide, which has got the formula N2O5. It is prepared by nitric acid with phosphorus pentaoxides. So when nitric acid is treated with phosphorus pentaoxides, it forms HPO3 plus nitrogen pentaoxides. It is a colorless solid with acidic character, and its structure is given. So that was all about the different types of oxides of nitrogen. The next compound that we need to discuss is about nitric acid. So its preparation in the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate and concentrated sulfuric acid in a glass retort. So when sodium nitrate and sulfuric acid reacts, it forms sodium bisulfate and nitric acid. On a larger scale, it is prepared by Austerlitz process. So in the industry, it is manufactured by Austerlitz process. It involves 3 steps. The first step is the catalytic oxidation of ammonia by atmospheric oxygen in presence of platinum or rhodium gas wire catalyst. So where ammonia reacts with oxygen to give you nitric oxide and water. Now in the second step, what will happen? The nitric oxide is converted to nitrogen dioxides. So when nitric oxide is treated with oxygen, it forms nitrogen dioxide. And the third steps we have got is absorption of nitrogen dioxides in water to get nitric acid. So the third step is the nitrogen dioxide that is formed is made to react with water to form nitric acid. So nitrogen dioxide plus water give you nitric acid plus nitrogen monoxides. The aqueous nitric acid can be concentrated by distillation up to 68% by mass. Further, concentration to 98% can be achieved by dehydration with nitric sulfur with concentrated sulfuric acid, and 98% nitric acid is known as fuming nitric acid. Properties of nitric acid: it is a colorless liquid. In the gaseous state, nitric acid exists as a planar molecule with a structure as shown below. The structure of nitric acid is this one. where we have got the bond angle of 102 degree with nitrogen and hydrogen, and the bond angle between two oxygen atom is 130 degree. In aqueous solution, nitric acid behaves as a strong acid giving hydronium and nitrate ions. So when nitric acid dissolves in water, it gives you hydronium ion and nitrate ion. Consider nitric acid is a strong oxidizing agent and attacks most metal except noble metals such as gold and platinum. The products of oxidation depends upon the concentration of the acid, temperature and the nature of the material. So nitric acid is a strong oxidizing agent and it attacks almost all metals except noble metals like gold and platinum. They cannot be affected by nitric acid. So when copper reacts with nitric acid, it forms copper nitrate, nitric oxide and water. When copper reacts with concentrated nitric acids, it forms copper nitrate, nitrogen dioxide and water. So just see the difference between dilute and concentrated. So when nitric acid reacts with zinc, it forms zinc nitrate, water, sodium zincate and nitric acid. Some metals like chromium, aluminum do not dissolve in concentrated nitric acid because of the formation of passive film of oxide on the surface. Concentrated nitric acid also oxidizes non-metals and their compounds. Iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid and phosphorus to phosphoric acids. So when iodine reacts with nitric acid, it forms iodic acid. When carbon reacts with nitric acid, it forms carbon dioxide, water and nitrogen dioxides, and when sulfur reacts with nitric acid, it forms sulfuric acid, and phosphorus reacts with nitric acid to form phosphorus acid. Next we have got a brown ring test. It is very important test. It is the test to identify the nitrate ion in any compounds. It is a test used for the detection of nitrates. The test is carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion. So the compound need to be tested, has to be taken in a test tube where you have taken the nitrate compounds, which one you need to identify, and to that we add dilute ferrous sulfate solution and then carefully adding concentrated sulfuric acid along the sides of the test tube. Then after that we will add concentrated sulfuric acid by sidewise. A brown ring at the interference between the solution and the sulfuric acid layers indicate the presence of nitrate ion in solution. So you will observe that a brown ring has been formed between the surface of the two solutions. So the reaction is nitrate reacting with iron to give you in presence of acid to give you nitric oxide, Fe3 and water, where a complex is formed. That is a brown ring. It is used in the manufacture of ammonium nitrate for fertilizers and other nitrates for use in explosive and pyrotechnics, for the preparation of nitroglycerin, trinitrotoluene and other organic nitro compounds, in the pickling of a stainless steel, etching of metals, and as an oxidizer in rocket fuel. So these are the uses of nitric acids. Next element we have got phosphorus. So we have got different allotropic forms of phosphorus. 3 allotropic forms we have got. So phosphorus exists mainly in 3 allotropic forms: white or yellow phosphorus we call, red phosphorus and black phosphorus. So these are the 3 types of allotropic forms of phosphorus. So you can remember the 3 allotropic forms, and phosphorus exists in P4 state. The structure is given as it is. Next we have got phosphine, PS3. Okay, it is prepared by the reaction of calcium phosphide with water or dilute hydrochloric acid. So when calcium phosphide reacts with water, it forms calcium hydroxide and phosphine. In the laboratory, it is prepared by heating white phosphorus with concentrated sodium hydroxide solution in an inert atmosphere of carbon dioxide. So in lab, it is prepared by reacting phosphorus with phosphorus with sodium hydroxide and water to form phosphine and sodium hypophosphite. The properties is, it is a colorless gas with rotten fishy smell and is highly poisonous. It is slightly soluble in water. The solution of PS3 in water decomposes in presence of light, giving red phosphorus and hydrogen. when absorbed in copper sulfate or mercury chloride solution, the corresponding phosphides are obtained. So when it comes in contact with copper sulfate, it is going to form mercuric, it is going to form the corresponding phosphides, that is copper phosphides and mercuric phosphides. Like NH3, phosphine is weakly basic and gives phosphonium compounds with acids. Phosphine is technically used to produce Holmes signals. Containers containing calcium carbide and calcium phosphide are fused and thrown in the sea. The gases evolve bond and serve as a signal. This is how it acts and function. It is also used in smoke screens, phosphorus halides. Phosphorus form two types of halide, PX3 and PX5. PX3 you can take it as PCl3 phosphorus trichloride and PX5 as phosphorus pentachloride. So we can prepare it by passing dry chlorine over heated white phosphorus. So when phosphorus reacts with chlorine, it forms PCl3. It is also obtained by the action of thionyl chloride. When phosphorus reacts with thionyl chloride, it can form PCl3 and sulfur dioxide. It reacts with organic compounds containing OH groups such as acetic acid, ethyl alcohol, to replace that OH group by Cl, which we have seen in the organic chemistry chapter. So when acetic acid reacts with PCl3, it forms acid chloride and hypophosphorus acid, and similarly when ethyl alcohol reacts with PCl3, it forms ethyl chloride and hypophosphorus acid. Structure, it has got a pyramidal shape as ammonia, in which phosphorus is sp3 hybridized. Next, PCl5 phosphorus pentachloride is prepared by the action of white phosphorus with excess of dry chlorine. So here we need to take a excess of chlorine, that will form PCl5. It is also prepared by the action of thionyl chloride on phosphorus. So when phosphorus react with 10 molecules of thionyl chloride, it forms PCl5. PCl5 is a yellowish white powder and in moist air. It hydrolyzes to POCl3 and finally gets converted to phosphoric acid. So when PCl5 reacts with water, it forms POCl3 plus HCl, and POCl3 when reacts with water, it forms H3PO4 plus HCl. When heated, it sublimes but decomposes on a strong heating. It reacts with organic compounds containing OH to give chloro derivative. So it has got the same function as PCl3, and we have seen the reactions between PCl3 and PCl5 together as well. In gases and liquid phase, it has a trigonal bipyramidal structure. The three equatorial PCl bonds are equivalent, while the two axial bonds are longer than equatorial bonds. This is due to the fact that the axial bond pairs suffers more repulsion as compared to equatorial bond pairs. So this is the structure for PCl5. So where you have got 3 chlorine atoms at an equilateral triangle and 2 on the axial side up and down. This is the structure for PCl5. Then we have got oxo acids of phosphorus. So here you need to study about you need to know about the structure. Okay, so phosphorus forms a number of oxo acids. The first is hypophosphorus acid, which has got the formula H3PO2. So H3PO2 has got the structure, this one. You need to know the structures only. The second one, we have got H3PO3, that is orthophosphorus acid, or we also call phosphonic acid, which has got the formula which has got the structure as shown below. Then we have got pyrophosphorus acid, hypophosphoric acid, and the structure is given as this one. Then we have got orthophosphoric acid H3PO4, which is also called phosphoric acid simply, this one. And pyrophosphoric acid, the structure is this one. Metaphosphoric acid, no need to see. This no need to see. Okay, so that is all about the group 15 elements. So whatever we have just seen, you need to study that much only.